This presentation will cover Chapter 12. Chapter 12 makes use of the chi-square distribution in order to test whether or not we've actually selected the correct distribution for testing our hypotheses. So remember, we've now learned several distributions. We've learned some discrete and some continuous. So the discrete distributions we've learned are binomial, Poisson, hypergeometric, and the continuous distributions we've learned are uniform, exponential, and normal. So we've seen quite a few. And the question can become, well, once I've gathered my data, how do I know what type of distribution it actually follows? And in order to know whether I'm conducting my hypotheses test correctly. So that's what we're going to discuss in this chapter. We're going to start with binomial or multinomial distribution. So this is where you had, in the case of binomial, you had two choices which your independent variable could take. This was like heads or tails, yes or no, Pepsi or Coke, something like that. Multinomial takes the same basic logic, except that you can take more than two options. So Pepsi, Coke, or Sprite, yes, no, or maybe, that kind of stuff. So we'll start by assuming that HO is true and develop an expected frequency distribution EI. Then we will compare our expected results with the actual observed frequencies from the sample that we gathered, and we will test our hypothesis whether or not we in fact did follow a multinomial or binomial distribution by comparing what we expected to see happen versus what actually happened. And we're going to do that using a chi-squares test. So if you'll notice, the test statistic that you're using is the difference between what you actually observe minus what you expected, that squared, divided by what you expected, and we're going to add those all up for all of the different observations. The chi-squares test that you run then will always be a chi-squares upper, so chi-squares alpha, or chi-squares of 0.05, if we're going to be 95% confident, is what we will always look at. So you'll always be looking up the same value in the table, and we'll reject HO if our p-value is less than or equal to alpha. Well, if you'll notice here, this is a right-tailed test, so we're going to be looking for the p-value upper. Okay? What you will notice is not listed here is the degrees of freedom, so make sure you write that down. Remember, anytime we're running a chi-squares test, we need to have degrees of freedom. In this case, it's not n minus 1. Degrees of freedom will be k minus 1, where k are the number of categories. So in binomial, that would be 2 categories. If it's trinomial, that would be 3 categories. If there are 4 categories, k would be 4, that kind of logic. So what exactly are we looking at with this hypothesis? We're testing, is this the right distribution? So HO, the population follows a multinomial distribution with specified probabilities for each of the k categories or outcome. HA, the probability does not follow a multinomial distribution. Okay, so HO is always we selected the correct distribution. HA is always we did not select the correct distribution. So here's an example. Finger Lakes Home manufactures 4 models of prefabricated homes: a 2-story colonial, a log cabin, a split level, and an A-frame. To help in production planning, management would like to determine if the various customer purchases indicate that there is a preference for any selected style. This is going to be a multinomial experiment where there are 4 choices or potential outcomes. Those 4 choices being a colonial, a log frame, a split level, or an A-frame. Now, interestingly enough, if we note here, there is no specified preference. It doesn't say, we expect to have more colonials sold or we expect to have more log homes sold. The way they've stated this right now, they haven't shown any sort of preference towards any kind of structure in particular, and they're asking us to determine whether or not there is a specific preference. So once we've gathered our data of our 100 customers here, we see that 30 homes were colonial, 20 were log, 35 were split level, and 15 were A-frame. Now, so that is our F, our actual observed number of outcomes. We need to compare that to our expected value. Now, since we're only asking, is there a preference, that means that there really isn't any given expected value for us. So in this case, since no probabilities are pre-assumed, we will assume that all of the probabilities are equal. Since there's 4 potential outcomes, that would mean that the probability of each of those different house types being selected would be 25%. Now, this could be slightly different in the review question that you'll see on there. They have listed probabilities that they already expect applied in there. So you would just use those as opposed to calculating a probability. So just look at the way the question is framed. So HO, we follow the binomial probability, or the multinomial probability distribution, where each of the expected outcomes has a 25% probability. HA, we do not follow the multinomial, and each of the expected outcomes is not 25%. So our next step is to develop our expected frequency distribution while assuming that HA is true. So if HA says each of our expected outcomes is 25%, we base our expected frequency distribution on that potential 25%. So here I've shown this calculation in 2 different ways. I've shown developing each of the expected values, just drawn out mathematically, and then I've shown it on Excel. So let's skip to Excel to see exactly what we're doing here. So here I have my observed data in the top. Observed data, 30 colonial, 20 log, 35 split, 15A for a total of 100. Since each of my probabilities is 25%, my expected probabilities is 25%, I will take the total, and I'll expect 25% will be colonial, and 25% will be log, 25% will be split, 25% will be A-frame. So that total observation, that 100, and that'll apply equally 25% across all 4 of my observations here. So you'll notice the 100, I F4'd that to make that constant. You will do that even if you had different percentages that were expected in here. You would just change them, so they wouldn't all be 25%. They would be whatever would be specified in the problem. Okay? So that allows us to come up with our expected data. So you can see here, I observe 30 colonials versus I expect 25. I observe 20 log versus I expect 25. I observe 35 split versus I expect 25. I observe 15A versus I expect 25. My next step is to compare my expected frequencies with the observed frequencies. And then I'm going to examine that using a chi-squares distribution. So don't freak out about the formula. All it's asking you is observed minus expected squared as your numerator divided by expected. Okay? Now here I've written it out again mathematically and then also in Excel. So I observed 30 versus my expected 25 squared, and I'll divide that by my expected 25. Then for log, I observed 20 minus my expected 25 log squared, and so on and so forth. And I add them all up to come up with a chi-squares value of 10. Here I've shown the Excel steps for that, so let's go back to our Excel. And you'll see each chi-squares observation. Now my total chi-squares is the sum of all of these individual observations, but each observation is equal to my observed minus my expected, that's my numerator, and I square that, divided by my expected. So I'm going to do that for each one. Now here, once you've set this up, you can actually just drag across. So I set it up for the first one, and then I just drag across to get each of my expected values there. And then I added them all up because the formula says the sum of the difference between my observed and my expected squared divided by my expected. So I add them all up and I come up with 10. Now in order to test this, I would look at the p-value upper. The p-value upper, remember, is chi-dist. So in order to do the chi-dist, I need my x, which is my chi-squares value that I calculate, comma, degrees of freedom. For the bi or multinomial experiments, the degrees of freedom is k minus 1, where k is the number of categories. In this case, there are 4 categories, so my degrees of freedom is 3. So I come up with a chi-squares value of 0.0185. Now I ask myself, is 0.0185 less than or equal to 0.05? And the answer is yes. Therefore, I will reject my HO. Okay? So that tells me what, oh, and I have it written out the other way as well, because this is a right tail chi-squares test. Also to reject, you could use look it up in the table, and you would reject if the value you get is greater than chi-squares for 0.05 and 3 degrees of freedom, which gives you 7.185. So once I rejected this, what does this tell me? Okay, this tells me, well, let's look at my HO. My HO was, we follow a chi-squares we follow a binomial distribution or multinomial distribution where all of the probabilities are equal, meaning that the customers do not show any preference for any particular type of house. Since I rejected HO, that means I'm 95% confident that HA. So my HA will tell me that the probabilities are not all equal. So that tells me that they do have a preference for different types of homes. And we can see from the data gathered that colonial homes are preferred. Or actually, in this case, sorry, split level homes are preferred because that has the highest observed percentage. So I would reject HO that there is no preference for different types of homes, and I would say I am 95% confident that consumers do exhibit a preference, and from my data it appears that they exhibit a preference for colonial or split, with split coming out slightly ahead. The next type is another bi or multinomial situation, but here we're looking across 2 different categories. So we're going to follow the same basic process, start by assuming that HO is true, and develop an expected frequency distribution based on that. Then compare our observed with our expected, run a chi-squares test on that, and reject HO if if your p-value is less than alpha, which is going to be 0.05 for a 95% confidence. Okay. Now, you'll notice that the equation looks slightly different here because it has a double summation. That just means sum over both I and J. So I indicating the row that you're using and J indicating the column that you're using. But again, we're following the same exact process. So let's look at our example. We're still looking at these prefabricated homes, but now we're looking at the number of homes sold for each model and price for the past 2 years. So for convenience, the price has just been broken down into 2 easy categories, either 200,000 or less or 200,000 or more. And I can see this cross-tabulation that's been developed. Now remember, you know how to create a cross-tabulation using Excel's pivot table function. Okay. So my first step is, let's examine my hypothesis. HO, the price of the home, is independent of the style of the home that is purchased. HA, the second HO should actually read HA, the price of the home is not independent of the style of home that's purchased. In general, when you're looking at these crosstabs, HO is that row is independent from column. HA, row is not independent from column. Okay? So here, your rows are the under 200,000 or over 200,000, and your columns are the house style. So HO, that price of the home is independent of the style, versus HA, the price of the home is not independent of the style or depends on the style. Okay, so now we are going to come up with our expected observations, and we're going to use this formula. The expected value is row I total times column J total divided by sample size. Now, it sounds complicated, but really all we're doing here is looking at our observations and saying, okay, well, if we had from our observed data, let's go into Excel so we can see this a little bit better. Example 2. We have from our observed data, and let me bring this back into taking out the formula view, sorry. From our observed data, we know that 55 homes were under 200,000 and 30 homes were colonial. So in order to get the expected number of colonials under 200,000, it would be 50 times 35 divided by 100. So it's just saying, look at the proportion that are under 200, so under the row amount, then look at the proportion that are under the column amount and divide that by your total value. So that's how we're coming up with our expected values. So again, the formula is row total times column total, and that numerator divided by your sample size. So for my expected data, okay, my column total is 30 for colonial, my row total is 55 for under 200,000, and my sample size is 100. So for this entire row of under 200,000, I can F4 my row total, and the only thing that will change in each one is my column total, right? And then notice that I also F4'd my sample size because that remains constant throughout all of my calculations. I do the same thing for the second column here. My row total will be over 200,000, so I can F4 that because that will remain constant for this entire row's worth of data, but the column totals will change. So in each case, I come up with my expected values. So I expect 16.5 colonials versus my observed 18. Okay. Now I'm going to compare my observed frequencies with my expected frequencies following that same basic process. observed minus expected squared as my numerator divided by my expected. Then I'm going to add those all up. Now this is slightly different because I'm going to need to add across my rows and down my columns. Now you can add, you can add down columns and then across, whatever works best mathematically for you, as long as you make sure you add up everything. So that double summation just means add across rows and columns. So make sure you have everything. So let's see how that calculation works. Okay, so for Colonial, I observed 18 versus I expected 16.5. That quantity squared divided by my expected 16.5. Moving over then to my log. Moving over then to my log, I observed 6, I expected 11 divided by that 11. Then moving over to my split, I observed 19, I expected 19.25 divided by that 19.25. And so I'm going to do this for across all of the rows and columns. Now the way I did this, I summed across my rows. So sum across my rows for each, and then I just added those two summations. You could, of course, sum down each of your columns and then add them here. Whichever way you want to do it, you will come up with the same number. This number is your chi-squares. It's your chi-square statistic. So according to our right-tailed test, we would reject if our chi-squares that we calculate is greater than the chi-squares value in the table. So the chi-squares value we calculate is 9.15, and you can look up the corresponding chi-squares value for a chi-squares of 0.05 with how many degrees of freedom. Okay, this becomes a question. Here, degrees of freedom is calculated a little bit differently. We need to base our degrees of freedom on both the number of rows that we have and the number of columns that we have. So our degrees of freedom is, and I can write this out here for you, degrees of freedom is 1 minus your number of rows. How many rows do we have? We have under 200,000 and over 200,000. So 2 rows times, I'm sorry, it was not 1 minus, it's, sorry, number of rows, which is 2, minus 1, times number of columns. How many columns do we have? Colonial, log, split, and A, so 4 minus 1. Now, in the technical terms, they're saying that this is n minus 1, where n is the number of rows, times the quantity m minus 1, where m is your number of columns. Okay, yes, you do need to put a multiplication sign in there. So here again, our degrees of freedom is 3. So I can go and calculate my chi-squares distribution. Remember, I use chi-squares upper, where x is that 9.15 chi-squares value that I've calculated, and my degrees of freedom is 3 for the quantity n minus 1, n being the number of rows, times the quantity m minus 1, where m is the number of columns. Now, since I ask myself, is 0.027 less than 0.05? And my answer is yes. Therefore, I will reject HO. So the assumption that the price of the home is independent of, so my HO was the price of the home is independent of the style of the home purchased. In other words, rows do not impact columns. Price does not impact style. I rejected that HO, so I can say I reject that price does not impact style, or I can say I'm 95% confident that the price does impact the style of the home that you select. Okay? And then here you can see I have just a slide of all of the Excel formulas that were used so that you can practice with this material again. Finally, the last type of distribution I will examine is my normal distribution. So here, my hypotheses are going to be based on the fact that my data follows a normal distribution with a given mean or standard deviation will be my HO, and my HA will be my data does not follow a normal distribution with that given mean or standard deviation. So the first logical step is to calculate the mean or standard deviation. So mean, add up all the values, divide by the number of observations. Standard deviation is the square root of the variance, and here my denominator is going to be n minus 1. So if you do the descriptive statistics, it's going to give you this value anyway. So, quick way to run that, you could run descriptive statistics, or you could use your STDEV function for standard deviation and your average function for mean. Next, I'm going to define the interval of values so that the expected frequency is at least 5 in each interval. Now, this is interesting because our normal distribution is continuous, and we need, in order to run our chi-squares test, we need to have a discrete value. So what we're going to do is break up our observations into different groupings. You kind of see this in the crosstab already, where you're breaking it up into, in the crosstab example we just did, into under 200,000 and over 200,000. So to be honest, this breaking it up into different intervals is honestly the hardest step. So you'll see there's a whole slide listing out each of the different steps involved here. And the key is that we must have at least 5 observations within each interval. So then I have the equation that you're going to use to develop the intervals. The mean plus or minus, depending on the z sign, plus or minus the corresponding z value times the standard deviation. Then we will record our observed frequencies for each interval, so see how many fall within those intervals. Next, we will compare our expected frequencies with our observed frequencies. So following the exact same logic we've been doing before, observed minus expected, that quantity squared divided by expected, and then compare the sum of those observed differences looking at a, p-value, looking at your p-value, and you'll reject if your p-value is less than or equal to 0.05. So here's our example that we're going to be using. Your textbook authors think they're funny, so IQ computers, and they're asking, is it better than HP? Because, one letter off in each, yeah, they think they're funny. Okay, so IQ Computers manufactures sells a general-purpose microcomputer. As part of a study to evaluate sales personnel, management wants to determine at a 5% level of significance if the annual sales volume, number of units sold by a salesperson, follows a normal probability distribution. A simple random sample of 30 salespeople was taken, and their number of units sold are listed below. So we just have a sample number of observations. Note this is continuous, anywhere between 33 and 105. So we'll calculate the mean and standard deviation first. You can just do this in Excel using average and STDEV, that's fine. Now it's important, you have to calculate that mean and standard deviation first because you state your hypotheses based on the fact that your data follows a normal distribution with that given mean and standard deviation. So HO, the population of the number of units sold, has a normal distribution with a mean of 71 and a standard deviation of 18.54. HA, the population of the number of units sold, doesn't have a normal distribution with that mean and standard deviation. So next is where we come to defining the intervals. Okay, this is where all the steps are. Now, the rule is that you must have at least 5 observations in each category. So we'll take the number of observations and divide that by 5. that makes sure that we have at least 5 observations in each category. So that's how we're going to start always defining our categories. Then, in order to find the percentage in each category, you'll take 1 over the number of categories. Now, why am I saying 1 divided by? Well, we're looking at the standard normal distribution. So the area under the curve is 100%. So 1 divided by the number of categories will give you the percentage in each category. Then we're going to use that to calculate the category percentage. Now you're going, wait, I just calculated the percentage in each category. What do you mean calculate the category percentage? So let's say you have 10 observations that, let's say you come up with 10 categories. So your percent in each category would be 1/10. Well, you need a percentage to calculate your z-scores. So what you're going to say, that 1/10, that would be divided into the lowest 10%, then the lowest 20%, then the lowest 30, then the lowest 40, then the lowest 50, then you'd be at 0, and then upper 50, upper 40, upper 30, upper 20, upper 10. So we need to calculate those given percentages. So calculate the category percentage means take that percent that you know that's in each category and use that to determine the percentage bounds for that category. So 0 to lower 10% or 0 to upper 10%, then 10% to 20% in both upper and lower, and so on and so forth. Then you're going to use that to calculate the z-score of each category using your norm inverse. And then you're going to put this together into this equation to calculate the upper and lower bounds of each interval. So let's look at our example here. We'll figure out the number of categories, the percentage in each category. Okay, so how do I get the number of categories? Well, number of categories is n divided by 5 to ensure that there's at least 5 observations in each category. So I used count to find n. Then the percentage in each category is 1 divided by the number of categories that you come up with. Okay, so let's go into Excel so we can see this more clearly. And we are here in example 3. Now you do have access to these Excel charts. So what I would suggest is even after you've watched this, you make sure that you can go through and replicate these. So make sure you've practiced this before you come to class where we do the review questions. All right, so here's my data listed in cell A4 through J6. So I calculate my mean using my average function, so average of A4 to J6. I then calculate my standard deviation using the STDEV function for A4 to J6. Number of categories is 6. How? I counted up that I have, let's see, I don't even remember how many observations I have. We could do that. Okay, I counted up that I have 30 observations. So my rule is I must have at least 5 observations in each category in order for my chi-squares distribution to work. So 30 divided by 5 tells me that I must create 6 different categories. Then 1/6 gives me my percentage in each category. So this tells me that I need to have 16.67% in each category. Okay, so now I'm going to move over and follow those steps. Oh, I've already followed the first 2, but I'm going to keep going. Okay, so calculate the category percentage in each category is equal to the category number times the percentage in each category. So I know that each category must have 16.67%, and I know I must make 6 categories. So I made a list, category 1 through 6, you can either type in the numbers 1, 2, 3, 4, 5, 6, or you can go through and highlight. So if I type in 1 and 2, and then I highlight this and drag it down, it will count to 6 for me, just a simple time-saving mechanism. Okay, so take each percentage and multiply it by its category. So this says my first category will have my bottom 16%. My second category will have my bottom 33%. My third category will be at the 50th percentile. My fourth category at the 60th percentile. My fifth category at the 83rd percentile, and then my sixth category by default is going to be my 100th. So that's going to take me all the way to the end. So I don't actually need to calculate anything in here. You can, and if you just drag that down, that will give you a 1. And that is perfectly acceptable if you want to have that in there. It can, however, get confusing when you're looking at your z values later. So in general, I just say that's the top. I know that if, I know that it must be my remaining 17% or 16.67% at the top end must fall in there, because everything less than that is 83% of my observations. So my next step is to calculate my corresponding z value. How do I get that? It's norm inverse of that percentage. That gives me the z value using the standard normal curve for 16%, then for 16%, then for 33%, then for 50%, then for 67%, then for 83%. Now, my interval. The equation says x bar, which is your mean, plus or minus z times the standard deviation. Okay? So my mean plus my z times my standard deviation. Now, what I do is I always just add them, and I make sure that my z is negative if it's in the lower half and positive if it's in the upper half of my probability distribution table. So I don't worry about whether I'm subtracting or adding, I just always add them. So if it's negative, that is in fact subtracting it, because logically you would subtract in the lower half of your distribution and add in the upper half of your distribution. So as far as the formula is concerned, you can always just remember to add it, and that's fine. Okay? So note there that I F4'd my mean and my standard deviation, and then I was just able to drag this down to get the upper end of the bottom half of my distribution and the upper end for the top half of my distribution. So let's talk about that when I figure out the observed frequencies. So these intervals that I've actually been given, my goal, I've divided this into 6 different intervals. So my first interval is my lowest, 16.67%. That cutoff to be in the lowest 16.67% is that interval number of 53. So I'm going to count if my observations are less than that interval value. Now, I was having some difficulty getting Excel to read my numbers in here. Normally, you can just click on the interval value instead of typing it in, but for some reason, Excel wasn't reading that number. So what I did is actually just typed in that value, so 53. Okay. So my bottom 16.67% is 0 to 53. So for my first interval, I count the number of observations between 0 and 53, and I come up with 6. My next interval is, now it says percentage 33%, but I only want to look at the values in that second interval, not the first and the second. So that 33% includes my bottom 16.67%. So notice when I'm calculating the number of observations, it's count if it's less than or equal to 63 minus those 6 that were already less than or equal to 53. Okay? So for these intermediate categories, it's always going to be count if the value is less than or equal to the interval value that you get minus count if less than the previous interval. Okay, so let me say that again. Make sure you're writing this down because this is going to be important. For your bottom and top, for your bottom value, it's count if it's less than or equal to the interval value that you have, your first interval value. So for category 1, count if it's less than or equal to your first interval value. Then for all intermediate interval values, it's count if it's less than or equal to that intermediate value minus count if less than your previous value, okay? Because you want to subtract off the interval that you've already calculated. So I will go on following that same process. Count if less than or equal to 71 minus count if less than or equal to 63. Then count if less than or equal to 78 minus count if less than or equal to 71. Then count if minus less than or equal to 88 minus count if equals less than or equal to 78. Now for my last value is 88 and above, or my 83rd percentile and above. So I will count if it is greater than that interval value. So remember, for my first one, I counted if it was less than that first value. For my last category, I count if it's greater than that final value. Okay? So the first and last are the easiest. They don't involve any subtracting. Just for the first, it's less than or equal to. For the last, it's greater than or equal to that value. It's the intermediate ones where you have to worry about subtracting off the values that you've already included. So that will give me my observed frequency in each group. If you really wanted to, you could go through and count by hand the number that are between 0 and 53, then count the number that are between 53 and 63, then count the number that are between 63 and 71, then count the number that are between 71 and 78, then count the number that are between 78 and 88, then count the number that are between 88 and, your final value of 105 or your max. So if you want to do that by hand, you can. With a sample size of only 30, that's not such a big deal, but make sure that you have that logic of what you're doing in your mind. So if you get stuck at this point, what I would suggest, I'm not going to give you any huge data sets for you to actually practice with. What I would suggest, if you're confused here, is actually going through and counting some yourself to make sure that you have that logic correct. Okay, then we're going to go over and compare that to our expected frequencies. Well, since no percentage is given in here, our expected frequency is just our number of categories divided by our number of observations. So it's equally likely to be in any of these categories. And that also is consistent with our hypothesis, because our hypothesis says the population number of units sold has a normal distribution with a mean of 71 and a standard deviation of 18.54. Basically saying that all of our salespeople are equal. There is no relationship between the number sold and which salesperson you were. There's no kind of relationship there. So in all of the ones that we test, the expected frequencies in all of the examples I will give you, I will tell you will be calculated in the same way because they will all be equal. okay? And then just, dumb luck, make sure that your expected frequency adds up to your number of observations, and so does your observed, because, if you're going to mess up, that's going to be your first clue that that happened. Okay, next step, and you can see I've put all of those Excel steps in there. Next step is to calculate your chi-square statistic. Okay, chi-square statistic is the sum of all of the differences between what you observed minus what you expected squared divided by what you expected. So same formula we've been using all along. So I'll go back to my Excel. So I observed 6 versus I expected 5, that quantity squared, divided by my expected 5. Then I observed 3 minus my expected 5 divided by that quantity squared divided by my expected 5, and so on and so forth, and I will add them all up. So I'll come up with a chi-squares value of 1.6. I will reject HO if my chi-squares alpha is greater than or equal, if the chi-squares that I calculate, which is 1.6, if that is greater than or equal to chi-squares of 0.05, now, with how many degrees of freedom? Okay. So, how do I get my degrees of freedom? Okay, let's look here. My degrees of freedom, again, is 3. So the way I got that is K minus 3 degrees of freedom. Okay, so K is the number of categories that I have, and then minus 3. So this degrees of freedom is a little bit different. The rest have always been something minus 1. This is K minus 3. So number of categories minus 3. So I had 6 categories minus 3 gives me 3 degrees of freedom. And I come up with a p-value upper using my chi-dist function of 0.65. I reject HO if that p-value is less than or equal to 0.05. In this case, it is not. So I do not reject HO. And there is little evidence to support rejecting the assumption of the population being normally distributed. Now, be careful. With a mean of 71 and a standard deviation of 18.54 should also be written in there. So not only are you saying that, yes, it is normally distributed, but also that you have the correct mean and standard deviation. That part is key. Okay, so now go back and make sure that you can do all of these review questions without looking at the actual Excel, but go through, obviously copy and paste the data onto there, but make sure that you can do this just looking at the steps provided, not looking at the Excel examples. And if you can do that, then you'll be ready for the review questions when we go over them in class.